Good afternoon, everyone, and welcome to today's specialized workshop on zinc in engineering with a special focus on zinc rich paint and zinc thermal spray. Today's webinar is hosted by the Africa Desk of the International Zinc Association. I am Shannon Derejo from Creamer Media's Contract Publishing. To start, we extend our thanks to Simena, who have arranged the CPD points for this webinar so that registered professional engineers can earn EXA CPD points by participating in the webinar. If you haven't submitted your EXA registration number when you registered, please be sure to send it to us afterwards. Before we begin, please be aware that we have enabled the question and answer function, so please post your questions into the Q&A box. You'll find this on the panel at the bottom of your screen. The panelists will answer as many of your questions as possible at the end of the presentations. We are recording this webinar and we'll be sending the recording to you when it's available. We are also streaming live to YouTube. You can interact with the panelists and other attendees via the chat box, which you'll also find at the bottom of your screen. Now, this is an interactive workshop, so please be sure to post your questions for discussion throughout the webinar. So let's get started. Our first speaker this afternoon is Simon Norton. Simon is a corrosion and failure investigation expert and manages the International Zinc Association in South Africa and Africa. He will provide a brief presentation on understanding zinc chemistry. Over to you, Simon.
Thank you very much, Shannon. Thank you very much. Good afternoon, everybody. Good afternoon, ladies and gentlemen. Thank you very much for attending this International Zinc Association presentation on zinc in engineering. I'm going to do a short revision course on the chemistry of zinc and its role in zinc's role in preventing corrosion. We thoroughly and strongly recommend that you look at all the roles that zinc could play in your design, in your consulting work as engineers, and in everything you do in all your sectors, whether it's in civil engineering, marine engineering, mechanical engineering, construction, or building. And there are, of course, other applications for zinc. You wouldn't like your construction or design to look like this. It's likely this was the failure of a decking system where de-icing salts got into the structure, attacked the reinforcing steel, and the entire building collapsed. What we hope to do with these seminars and webinars and with today's is to show you how you can use zinc in its powerful role to protect against corrosion. Now, zinc in the periodic table is located in what we call the post-transition metal area. The transition metals, the most famous of which are cobalt, platinum, palladium, nickel, copper, silver, and zinc, cadmium, and mercury are what are known as the post-transition metals. Zinc is an atomic number of 30, and it's got 4 stable isotopes whose average atomic weight is 65.38. The number of electrons in zinc is 30, the number of protons is 30, and if you subtract the atomic number from the atomic weight on the right, you will get 35. That's the number of neutrons. Zinc's physical state is a solid. Its crystal structure is hexagonal, and its high valence, or what it's known as its oxides, have both acid and base properties. And this is absolutely vital to understanding how zinc works when you use it in its role as an anti-corrosion protection mechanism. By its electron configuration, which is actually the configuration of argon in the square brackets. And I just want to show you there's the argon configuration. And that would be 1s2, 2s2, 2p6, 3d10, 4s2. Now, each of these levels, 1s2, 2s2, 2p6, 3d10, that's the third shell. And in the D shell, there are 10 electrons. There are no empty spaces. And then you get 2 electrons in the 4th shell. This makes zinc particularly easy to ionize. In other words, it loses these 2 electrons, and its main form in which it's found is in zinc +2. So when you find it as a mineral where we pull it out of the ground and then treat it to produce pure zinc, it's found as sphalerite or zincite or franklinite or calamine. and smithstone. And if you look, sphalerite with galena and chalcopyrite on the left, and sphalerite as it's immersed in dolomite, another type of ore, and you'll see that it contains 5 to 15% of zinc. And it's out of these ores in South Africa, we have zinc sulfide ores. We have a particular problem in South Africa that our zinc sulfide ores contain, I suppose you could call it contamination with manganese, and that makes the process chemical engineering quite difficult. However, I'm not talking about geology here, I'm just giving a bit of background to its chemistry. Now, critical to the chemistry of zinc, and Graham Stead is going to be talking about that with respect to zinc rich paints, and Martin Gagne with zinc thermal spray. Critical to this is what we call the galvanic series. Essentially, when you coat zinc onto steel to protect it against corrosion, what you're actually doing is you sacrifice the zinc and you protect the steel. And the reason you're doing this, or how it works, is that the zinc forms an anode and is slowly eaten away and lost. And therefore, the thickness of the zinc coating is what's critical to your corrosion protection. And if you look at this table, this graph or this graphic here, the galvanic series, if you look at the top here, you'll see there is zinc, and it's the least noble of the materials that are on this series, the galvanic series in seawater. And then further down the series in the table, you'll see various other materials. You'll see cast iron and steel, for instance, sit over here. So there's a difference between the two. So when you combine zinc with steel or cast iron, let's take steel and zinc, you'll sacrifice the zinc because it's least noble compared to the steel. Just as an aside to you as engineers, be aware, and in fact, beware. Not only be aware, but beware. If you have active stainless steels and you combine them with materials that sit up, or either sit down here or sit up here, you could have a galvanic cell. So it's very important to make sure that when you're applying or using stainless steel, that it's in the passive form. In other words, that it's exposed to oxygen, oxygenated water, oxygenated wastewater, or to seawater in particular that's highly oxygenated. But let's move on and keep back. Let's just stick to zinc. If you look at this particular graphic, you will see at the top of the graphic that this is a representation of voltages with respect to silver chloride. So what we do is we take a reference electrode, in this case silver chloride electrode, which is a silver chloride material inside, silver in a silver chloride solution, and we measure the potential of zinc with respect to that reference point. There are others, but in this one we're referring to silver chloride. So you can see that zinc's sitting over here and mild steel is sitting over there. So there's quite a big difference in voltages between the two. Now, although you might think in terms of what I call gross large-scale engineering, that these are tiny values, they make a massive difference. So the difference between minus 0.6 of a volt and 0.1 of a volt or 1 of a volt is huge. If you turn it into millivolts, we're talking about the difference between 1,000 millivolts and 600 millivolts. These sort of difference make up what we call electrochemical corrosion cells. And this is all the basis of electrochemistry. If you look down here where my marker, my laser pointer sits, you'll see that there sits passive stainless steel. So if you are mixing passive stainless steel with something up here, then you're going to get a galvanic cell. And you're going to get a big difference. So then you've got to make sure that you isolate the two and that there are no electrodes. But our main point, and the main point of what I'm telling you, is that zinc sits here and it's the least noble or anodic of these materials. And over here sits mild steel. And you can see the voltages from minus 0.2 or 200 millivolts down to 500 millivolts. But look at where zinc sits, right over this side. So zinc is going to be sacrificed as least noble material. That's what we'll be discussing later when they talk about the zinc-rich paints. Now, as I mentioned earlier on, zinc has got a peculiarity which you need to watch out for. If, for instance, you use a galvanized roof that isn't coated, or a hot-dip galvanized steel structure, and you use it in a wastewater treatment works, If that wastewater treatment works liquor or water becomes acid, then you will get a reaction between the acid, the zinc oxide, and a base. Sorry, if you've got a basic solution, which is quite possible because wastewater can vary depending on what's dumped into it by the users. If you've got zinc oxide playing an acid role and you get a base, you're going to get a reaction of acid and base, gives you salt plus water. So you're going to start attacking the zinc. Equally, if zinc plays the role as an alkali, where you see my cursor, my laser pointer, and you've got hydrochloric acid, and let's say you've got an acid medium, let's just say for argument's sake that a factory in an area of South Africa near to the wastewater treatment works dumps a large slug of acid by chance or through an accident or a release by mistake into the wastewater treatment system. And you have zinc galvanized steel structures working in those wastewater treatment tanks, you're going to get a reaction and you're going to get attack on the zinc. It also happens on galvanized roofs, continuous galvanized sheeting, and so on. So you need galfan, zinc coated, if you're using zinc rich paints, thermally zinc, if you thermal spray with zinc, you'll have the same type of reaction. So today we're focusing on the protection provided by zinc to steel by means of zinc rich paints and zinc thermal spray. And the key chemical element is zinc. This is just an illustration of an operator, a skilled operator working to carry out zinc thermal spray, which Martin Gagne is going to be talking about. And then later on, these are a variety of zinc-rich paints. And you can see the variety that's offered. And I must tell you, if you look at the top right-hand photograph, zinc-rich paints are not cold galvanizing. When you galvanize steel, you form a range of iron-zinc alloys, and there's a metallurgical bond between the galvanizing and the steel. When you use zinc-rich paints, it's by adhesion and mechanical adhesion. But Graham will talk about that in a minute. You need to make sure you use zinc to protect against corrosion. It provides a powerful protective mechanism, and you won't end up with something like this. As you can see, there's a fair amount of corrosion there, and you can see the rebar inside this concrete looks rather thin. But if that had been galvanized, it's unlikely this event would have taken place. You can also carry out zinc thermal spray to protect your reinforcing steel or other steel structures. And this is another example of an operator doing such a job. When zinc is inside concrete and you use reinforcing steel, before it's coated, there on the left-hand side is the pH greater than 12.5 in concrete. In cement, obviously, it has that pH. The rebar is inside here, and this is a passive structure. Then with time, your concrete gets carbonated by carbon dioxide from the atmosphere, particularly at the coast, or if it's an area where there's high winds. If it's the coast and it's marine, there's going to be chlorides. And if you look here and you take the depth of concrete and you take the concentration of chloride, there it's high. And as you go into the concrete, it gets lower and lower. So initially, this pH here will change, but this part of the concrete is safe. But over a longer period of time, there's more concentration of chlorides, more oxygen reaches the center, more CO2, and you start to have an active corrosion cell. That's where zinc comes into play. And zinc chemistry, if you take your rebar and you galvanize it before you put it into concrete, you will then have a much longer life out of your rebar. Just a short revision. The electrochemistry of the corrosion of steel in water, or in an aqueous, as we call it, an aqueous solution. There's always a corrosion cell available that happens or occurs where zinc or corrosion takes place. And in particular with zinc, you'll have an anode. With steel, you'll have an anode and a cathode. But that applies to other corrosion as well, on aluminium, on copper. I'm just using the example of steel because we're going to coat it with zinc. So at the anode, iron is oxidized to what we call ferrous, the ferrous ion, ION. So iron naught goes to iron plus 2, and it generates 4 electrons. Those electrons are then transferred across to the cathode. And on the surface of steel, there are thousands of anodes and cathodes, and they're all reacting simultaneously. At the anode, you have what's called oxidation. You lose electrons. And at the cathode, you have what's called reduction. So here we've got oxygen being reduced to the hydroxide ion. That reacts with the ion that's formed here, the ions in solution, and you get iron hydroxide, iron oxide, and you get corrosion. And slowly, your steel or your material is taken and disappears. That's where zinc comes in. Zinc coated on the surface protects it. If you look at this graph briefly, you'll see that over time, if you've got an uncoated or unzinc coated reinforced steel, you will get to the point where it cracks. If you galvanize it and coat it with zinc, or you zinc thermal spray it, or you even zinc rich paint coat it, then you'll get a much longer life out of your reinforcing steel. Now, let's look at the chemical impact of the atmosphere on a zinc-coated steel. Now, this steel might be your ship superstructure. You have zinc thermally sprayed it, or it might be a warship missile launcher housing, and it's been zinc thermal sprayed, maybe even zinc-rich paint coating. Mine shaft support structure. You didn't galvanize it, but you decided you better protect it, so you called in spec coats and they carried out zinc-rich paint coating. Or a dockside crane where during maintenance you used either zinc thermal spray or zinc-rich paint. So here's an example of a warship. This looks like an Italian manufactured gun. It's got a housing. This is probably made out of composite material, but the rest of this material was all made out of steel, and it all could be zinc thermal sprayed or zinc-rich paint coated. So there's an option here to put zinc on it. It's exposed to the atmosphere. So that's what I'm discussing. This particular trawler has been completely covered with zinc underneath the top coats. Again, here you would be exposing, as the steel is, if you scratch the steel or if it's damaged, there'll be zinc exposed to the atmosphere. What actually happens there? Well, this is what actually happens. We're not talking about galvanizing at the moment. We're talking about just zinc. Zinc-rich paint as thermal spray. Well, it first forms zinc oxide and zinc hydroxide. Then it reacts with the carbon dioxide in the atmosphere to form zinc carbonate hydroxide and with the oxygen in the atmosphere. Then, because it's at the sea and there's salt spray, it reacts with the chlorides, and you then get zinc chloride hydroxide in this quite complex molecule. And then finally, the sodium gets involved, the zinc is involved, the chlorides, and even some sulfates from the sea. And you get this over time. This is what you get when you expose zinc to the atmosphere at the sea. On the right-hand side is a model that was developed by Gilders, and it's quite a useful model in that you've got a solid zinc coating, zinc-rich paint or zinc thermal spray. You've got anodes and cathodes on the surface, and this is called the electrodic area. And then slowly, with time, these compounds that I showed you on the left start to deposit on the surface. And how do they form? Well, the atmosphere is the gas. There's an interface with the liquid, say the seawater, and you get oxygen from the atmosphere, water from the sea, sodium chloride from the sea, sulfur dioxide from the sea, and carbon dioxide from the atmosphere. And all of these together form a very complex deposit on the surface of your zinc. And this deposit is what determines what happens to your zinc when you expose it to the atmosphere. So in your design, in your thinking, in your project, you need to think this out very carefully and decide, how are you going to deal with this? Are you going to put zinc on only in, say, a zinc-rich paint, and then or are you going to zinc thermal spray, or are you going to put other organic layers on to keep out all these materials? That's your design decision. We can help you with that. So if you look at this brief little box model, you'll see that on the left-hand side, zinc oxide hydroxide is formed. The atmosphere then forms zinc carbonate hydroxide over a period that goes up to days and weeks. And then with time, if you were exposed to sulfur dioxide sulfates near the sea, or a power station or coal-fired power stations, you'll get these compounds. And if you were exposed only to the atmosphere at the sea, you'd get this compound sitting over here. And how you use this knowledge will determine how you design your structure, protect it, using what the other expert speakers are going to be talking about. There is a model that's been developed for European Union atmospheres, and I would imagine that it could be used in South Africa relatively easily. You need to measure how much SO2 is in the atmosphere. The relative humidity you can measure easily with an instrument. The temperature equation, you can just measure the temperature yourself. The pH you can measure by measuring the rain pH. And the nitric acid, well, there's very little in our atmosphere, but if you can measure it, you do. Otherwise, you just make that term 0. And there you get the average corrosion rate in microns in 1 year. It's quite useful. So we're talking about zinc. It could be zinc on galvanized steel. It could be Galfan, which is an alloy of zinc and aluminium, 5% aluminium, the rest 95% zinc, or it could be pure aluminium. And here are the corrosion products that form when you have atmospheric exposure of these materials. Our aim at the International Zinc Association is to guide you and assist you in making a choice such that your product or your project will last as long as possible, and that you'll get a massive life, and that there'll be limited capital expenditure, and that maintenance will be kept to a minimum, and that you'll get a long life, longer than you would if you had not used a zinc-based product. You can either have bare zinc, which is on this side over here, or you could have Galfan in the form of wire, or Galfan-coated roofing or sheeting, very powerful product, or you could have bare aluminium. I'm just trying to give you some examples of how this reacts in the atmosphere. Now, Graham Stead's going to be talking about zinc rich paints, but I'm just talking about the chemistry of it. You get an anode and you get a cathode, and you've got a hole in a zinc coating. The zinc then forms materials that zinc oxide, hydroxide, zinc carbonate, and this little hole fills up. And by this action, eventually the coating protects the underlying material. If you only have a paint, a conventional, ordinary, run-of-the-mill paint, when the paint cracks or is damaged, then you've got the steel exposed to the atmosphere, corrosion forms, the paint then is peeled away, blisters and comes away, and the life of your machine, product, whatever it is shortened. So there you have it, a quick chemistry lesson on zinc and how its chemistry allows it to protect steel. I welcome any questions. You have our email address. You can contact me at any time, also our expert speakers. And I now hand back to Shannon. Thank you very much.
Thanks very much, Simon. I'm sure the engineers in the audience found that very informative and a good refresher of their zinc chemistry. So speaking of chemistry, I'd like to introduce our next presenter, Graham Stead of Specialized Coating Systems in Johannesburg. Graham has long experience in the paint and coatings industry. He holds a degree in chemistry and is presently the technical director of Specialized Coating Systems, which he co-founded some 22 years ago. He has previously worked for several major paint companies, including Kansai Plascon, specializing in heavy-duty coatings. Graham will now discuss zinc-rich paints. Over to you, Graham. I'll just ask you to unmute. There we go. We can hear you now.
Can we go for this? Yeah. Can you hear us?
We can hear you and we can see your presentation.
Good afternoon, ladies and gentlemen. Welcome to our presentation. It's a pleasure to be with you this afternoon. I'm talking about zinc-rich paints in engineering. The very famous, the late Sir Jan van Einsbergen, who we knew quite well in South Africa, coined the phrase, save the surface and you save all. I think that's what Simon's been talking about. An example of the onset of corrosion. And we probably don't even think about what is going to happen to that fixture. But I can assure you that in years to come, it'll be a pile of rust. And if you ever want to take that nut off, you'll have to cut it off. I've seen some devastating consequences of corrosion in Mozambique after neglect during a 20-year war when I worked on the Maputo and Beira harbors, and whole rafts of wharfs have just collapsed into the sea due to neglect. And human beings are a little bit like white ants. We keep on fixing stuff and keep it going. If you stop your maintenance, it falls apart quite quickly. Okay, Simon has covered this, the reactivity series of metals, and I just thought I'd show you a standard hydrogen electrode against which those previous values are measured. That is a 1 molar solution of hydrochloric acid and with hydrogen gas infusing into a platinum electrode. And the salt bridge, which is here, is connected to the zinc or the iron or whatever else you're measuring at the time. Just to recap, how can I get rid of this? Okay. Galvanic cathodic protection or active protection arises from zinc, the anode, sacrificing itself in favor of the base metal, steel, the cathode, with the resulting flow of electrons preventing steel corrosion. In this way, the protection of the metal is achieved until the zinc layer is eventually consumed. The term galvanizing embraces a number of processes whereby zinc is applied to steel for corrosion protection. These include the relatively thin coatings applied by the continuous process to galvanize sheet and wire, extremely thin zinc coatings applied by electroplating, and the substantially thicker and hence more durable coating consisting largely of corrosion and abrasion-resistant iron zinc alloys associated with hot dip galvanizing of structural steel and related components, including fittings and fasteners. Now, this process happens at the temperature of 430 odd degrees Celsius, and no other process can build up those very important iron zinc alloys, and let nobody convince you that zinc coatings can do the same, but zinc coatings can make up in other ways. Another method of applying zinc to steel is by means of the well-known thermal spray process, which we're going to learn about shortly. Mechanical plating is produced by impact from small beads, which are tumbled together in a barrel with zinc powder and cleaned workpieces. No heat is involved in this process. And sheridizing is a hot process where chemically clean products are tumbled in a barrel which contains zinc powder and sand. The process is carried out at a temperature of about 370 degrees Celsius, some 50 Celsius below the melting point of zinc. The result is a hard, uniform, abrasion-resistant coating consisting entirely of iron zinc alloys. And this is very effective for fasteners, which are generally not galvanized because of hydrogen embrittlement and the danger of progressive cracking. Zinc is an unstable metal which reacts readily with its environment, and the property that gives zinc its corrosion resistance is its ability to form a protective layer which consists of its own corrosion products. Once the protective layer has formed and completely covered the surface of the metal, corrosion proceeds at a substantially reduced rate. Zinc forms an amphoteric oxide with the result that both acidic and highly alkaline conditions adversely affect its corrosion resistance. So Simon has very eloquently elaborated on that. Life expectancy of zinc-coated steel. These were taken from American figures, which I have converted here into weight per square meter. And in this country, Z175 galvanized steel means 175 grams of zinc per square meter, both sides. And that results in a relatively thin coating, and in years to failure, we're talking about 8 to 10, and on the cheap galvanized sheeting, it's down to 60 grams per square meter, and that is very vulnerable to corrosion. And these are minimum. This is IZA 1461 mean coating thicknesses for the various thicknesses of steel. So just a little bit of the history of the zinc coatings. The recognition of bimetallic couples, electrochemistry, electroplating, and the electrochemical theory of corrosion happened in the late 18th century. Protective value of electroplated zinc on steel was recognized, and the hot dip galvanizing was gaining acceptance by the middle of the 19th century. Zinc powder paints were first introduced to prevent linseed oil paints from peeling from hot dip galvanized sheeting. The mechanism was the finely dispersed zinc particles reacted and absorbed the low molecular weight organic acids, which are the byproducts of the drying of the linseed oil film. These early paints were never a success. Well, the first thing I learned in the paint industry is that you never put alkyd paints on galvanized sheeting, because the oxides saponify the oils in the alkyds and form a soap. Saponification is the formation of a soap, and that soap layer forms a very efficient release layer for the paint. It's very, very good business for the paint industry, actually. Little progress was made until post-World War II years, until the talented team under Dr. Evans in the Cavendish Laboratory at Cambridge University did basic research on zinc powder coatings, and several important things happened. The zinc metal industry became capable of manufacturing powder of higher purity and uniformity of particle size. Now that is very important. Epoxy resins and non-saponifiable polymers such as polystyrene became commercially available. And polystyrene has been superseded by very much more stable polymers such as acrylics and vinyls and many other polymers. And then ion exchange clays capable of giving non-viscous gels and organic solvents help to solve storage and application problems. Because of the density of zinc, the high density of zinc, it sinks like a stone, and one has to keep it in suspension and supply a can that can be reconstituted by stirring in a relatively short time. And then ethyl silicate, which had been produced in tank car quantities during the war to produce ethanol and propanol solid fuels, and as a mold binder in the lost wax casting process for high performance alloys, became a surplus commodity. And in the paint industry, we are governed by the availability of raw materials. In present times, epoxy and epoxy curing agents are in very short supply. And this is where inventiveness takes place and you find substitutes. The next thing that happened is that the price of steel went up. So it was very much more worthwhile protecting it. And then the stage was set for the rapid development and ready acceptance of zinc rich coatings as we know them today. A comparison of various zinc coatings. It should be noted that each coating has its strengths and its weaknesses. So hot dip galvanizing, for its generally high performance, which has been proved over many years, especially in duplex systems. Duplex systems, those are the coatings that cover galvanizing, must be the subject of another webinar. It's a very complex subject. And its ease of application on small parts, its penetration and coverage of the corners, and its relative independence of the human element in obtaining uniform film thickness. And those two wonderful things about hot dip galvanizing must never be forgotten. It builds up on edges and it reacts uniformly in that hot environment. And it is very difficult for the coating industry to reproduce that evenness. Silicate types for maximum temperature. These are the inorganic zincs and the alkali silicates. Maximum temperature resistance, 400 degrees C. Maximum self-weathering and excellent resistance to handling and erection damage. Ease of top coating for large and awkward shapes or sub-assemblies which are not suitable for galvanizing. And often a structure will not fit into a galvanizing bath, and the size of the baths is the limitation in many galvanizing plants. These ethyl silicate-based inorganic zincs, these products are either supplied with the zinc as a separate powder component to be added and stirred in immediately prior to use, or as two components with the base containing the already wetted zinc and the ethyl silicate, sorry, that's a mistake, should be ethyl silicate as a second curing component. They are applied to brazier blasts, clean steel of an SA3 blast standard and from 50 to 70 microns blast profile to a dry film thickness of 70 to 90 microns. Now the preparation of steel to SA3 is a controversial subject, and that is in fact why a standard of SA2.5 was adopted, because the contractors argued that it was not practical and very expensive to achieve an SA3, which is a clean blast. So SA2.5 is slightly lower than that, but I emphasize that the quality of the preparation is of utmost importance, and the dedusting and quick overcoating of the blasted surface is of paramount importance. They can be overcoated by a second coat after becoming touch dry, 30 to 45 minutes, or can be applied as a thin first coat, followed by a full coat. They cure with the zinc, forming silicon zinc silicon lattice. Thus, the inorganic part, the inorganic nomenclature, and ethyl alcohol is released as a reaction product. So there's no carbon in the resultant film. As the silicates are glass-like binder, the resultant coating is hard and very adherent. If the cured surface is rubbed with a coin, it produces a shiny zinc appearance. The exposed zinc surface reacts with atmospheric water and carbon dioxide to produce zinc salts, carbonates, and all the other salts that Simon was talking about, which densify the surface and add to the impermeability of the coating. And the coated steel items can be transported soon, 24 hours after coating, and with low risk of damage. So in the 80s, we ran a contracting company during the situated in Wadeville during the building of Cecil 2 and Cecil 3, and we were fortunate enough to collect the contract for blasting and coating the structural steelwork with inorganic zinc. And these were products like Available Zinc 7, which we made under license at the time, or Plascon paints made under license at that time, or Zinc Galv 6 from Dulux. And it was a very efficient process, and we could process as much as 100 tons in 24 hours. This business went on for about 3 years. The coating can be exposed in non-polluted inland environments for many years, or alternatively be overcoated with a suitable top coat system for more corrosive environments. These types of zinc-rich coatings have been used successfully for the last 60 years with good results. And inorganic zinc overcoated by epoxy has been recorded to last 20 years in a tropical marine environment in the splash zone. Zinc-rich coatings provide cathodic protection, whereas regular paints protect by forming an impermeable barrier between the metal and the atmospheric moisture. The cathodic cell protects the steel at the expense of the zinc. Zinc coatings also provide some barrier protection to the surface. I emphasize that the surface preparation must be as good as possible, and the surface profile should not be too high. I would say 50 to 70 microns maximum, depending on the final specification. Cleanliness, lack of oil on the surface, lack of dust on the surface. One needs to get the zinc particles in contact with the steel particles as quickly as possible. Although zinc-rich coating can be used as a standalone coating, it is often top-coated with a paint or epoxy. So there's a whole discussion on duplex coatings for, for zinc-rich coatings, as opposed to the discussion of duplex coatings for galvanized, hot-dip galvanized. This primer provides a backup or additional method to protect the steel from corrosion under a top coat of epoxy or urethane paint. There are two types of zinc coatings: inorganic. Okay, this is just a repetition. Inorganic coating, zinc coatings must be applied by spraying. Inorganic zinc coatings provide better steel protection than non-top coated organic zinc coatings when not using a top coat. Organic zinc coatings are normally applied by brush roller or spray. When not using a top coat, they do not protect the steel as well as an inorganic primer. Organic zinc coatings do provide the same degree of protection as inorganic coatings when the coating is top coated. Organic zinc coatings can be a moisture-cured urethane zinc primer, which is easy to apply to a surface. Now, I must emphasize that the spraying process must include agitation of the pressure pot or container where the zinc is the catalyzed, or the single pack zinc is being sprayed from, because the zinc will tend to settle, and one must have the correct amount of zinc in the spray line at any one time. Some popular applications for zinc-rich coating systems. We're running a bit short of time, so I won't elaborate on this, but this is common sense. Highway guardrails. In America, they call them Armco rails. Well, Armco is a big galvanizing company in this country. Bolts, these things we're very, very familiar with. These are products that we sell. The ZincFix Original is a product I developed about 23 years ago after discussions with the doyen of the galvanizing industry in this country, Walter Barnett, who was heading up the Hot Dip Galvanizers Association at the time. And I said to him, wouldn't you like a small pack of high zinc containing repair material for the galvanizing industry to fix up scratches and defects in the galvanizing? And he pounced upon the idea, and we developed this product, which originally was a 3-pack product because I was not sure of the stability of the zinc in the epoxy component or the curing agent component. I would never have put it in the curing agent component because the amines are very alkali. So the original ZincFix packets were 3-pack with 2 seals, and it was a bit of a laborious procedure to first mix the zinc in by squidging it around into the base and then opening up the seal and letting in the curing agent. And we had a pot life of about 30 minutes, which enabled somebody to open up the packet and squeeze out the mixed zinc and apply it to get the surface to be protected. Anyway, that has progressed to a 2-pack. We now disperse the zinc using new wetting agents and dispersants. We're able to squeeze more zinc into the epoxy, and the resultant is not more than 80% zinc. But this has been a very, very successful product and is used extensively in the galvanizing industry. We have literally sold hundreds of thousands of units of this product. And this is it in use. And we supply it in 100-gram packets, which is only about 30 milliliters. And that is about all you can apply from a packet in that short time. And the galvanized items out of the zinc bath are always containing scratches and things from the hooks that they pull in out and guide the stuff off the cranes with. And if you left them, they would form rust spots. And ZincFix has solved that problem to a great degree. So here are the advantages of the squish pack. Easy, accurate mixing of small packs ensures 100% pure and reduces wastage. And when you're using such small quantities, you cannot use 2 containers because some activators always left in the activator container. You do not get an exact mix. And the product is resistant to 1,000 hours humidity and 1,000 hours salt spray resistance. And I once did an SABS evaluation of ZincFix against galvanized panels. And let me tell you, after 1,000 hours salt spray, the galvanizing was not in good condition and the ZincFix was still in pristine condition, but that was 400 microns thick. Okay, then we go on to ZincFix 90, organic bound zinc rich film, 96% zinc in the dry film. And this is where I said you have to agitate the zinc while applying it, especially by spray, because if you use roller or brush, it's being agitated by the implements. It's used as a protective coating by creating a cathodic sacrificial barrier offering comparative features to hot dip galvanizing in the form of liquid applied coating. It has the advantage of infinite recoatability with minimum preparation requirements, and suitable as a coating for structures too obscure, too large for molten zinc baths. Okay, that's just a description of its sacrificial properties. And some of the items to which it is applied. Electricity, high tension masts on the right, and the central picture here is in the Gautrain tunnels. They found in the Gautrain construction where the excavations went down to 90 meters, everything below a certain level started to corrode, even the galvanizing. So ZincFix was used extensively to overcoat it. Excuse me. The time is up, but I just wanted to mention new innovations. Zinc Flake is now available on the market and is very useful, and you can reduce the amount of zinc in a zinc rich paint and get the same corrosion resistance. That's just a description of a patented method. I got this off Wikipedia, where high strength steel parts such as bolts and strength with those strength categories and components are susceptible to hydrogen embrittlement, and this galvanic coating process solves the problem. And this is the patent mentioned with the thin film thickness of 8 to 12 microns. And the zinc flakes coatings do not create any hydrogen in the process. They were used for critical applications and an alternative to electroplating. So these are developments with zinc coatings that are going on all the time. It's a very big subject, and we could go on talking for some time further. Those are my acknowledgements, and I thank you for listening. And if there are any questions, please indicate. Get back here.
Thanks very much, Graham, for your insights on zinc-rich paints for corrosion protection. I'm just going to stop sharing that screen now. Before we continue with our final guest, who is Martin Gagne, I would like to remind you all to send us any questions if you would like the panelists to answer any of your questions. And then I'm going to share with you a survey now. I'll keep it on the screen for a while, just so that you can answer that at your leisure. You can move it around your screen as well if it's blocking any views or anything, but I'll keep that up for the time being. It's basically just to find out if you recommend zinc-rich paints for projects, if you specify zinc-rich paints, do you use inorganic or organic zinc-rich paints? Have you ever specified zinc thermal spray for steel on your projects, which is what we're going to hear about now from Martin? Are you considering zinc thermal spray for a marine application? And then if you would like the IZA to contact you regarding the selection of a zinc coating, you can send us your details in the chat. And then if you would like a specialized coatings to contact you regarding zinc rich paints for a project, you can also send us your details. So I'll leave that poll up. And then while you fill that survey in, I would like to introduce our final guest. And that is Martin Gagne, who joins us from Toronto in Canada. Martin is involved in the IZA's global programs in general galvanizing, die casting, and zinc oxide. He began his career as a research engineer at Dofasco Inc., then served as manager for market and product development at Noranda Falconbridge, and most recently for Xstrata Zinc Canada. Martin will provide a detailed overview of zinc thermal spray and its application to engineering. So Martin, the platform is yours.
Well, thank you very much, Shannon. And yeah, pleasure to be here from virtually from Toronto. So I will just put my screen up now, and I hope everyone can see that. But I will be talking specifically about thermal spray zinc metallizing. I'll give a brief introduction to the International Zinc Association. We've already had a good overview about how zinc protects steel from corrosion, so I can go through that briefly as well. We'll look at some of the corrosion conditions in South Africa, and then we'll go more into detail in the thermal spray zinc coating process, and we'll finish with some case studies. Now, the International Zinc Association works around the world to protect and grow existing zinc markets, develop new markets, but also to transfer best practices and technologies. I'll be showing some case studies from Norway, where they have been using thermal spray zinc on bridges since 1965. Uniquely, every steel bridge in the country is protected with thermal spray zinc, and with fantastic results. Some of those bridges are 50 years old now with no maintenance, and they're expected to last 100 years. So this is a best practice we would like to transfer to other areas. South Africa is one, also has a coastline similar with Norway, and I think could benefit from using zinc to improve the corrosion protection of steel structures. So we will be talking about thermal spray zinc. We're all familiar with hot dip galvanizing. This is the full immersion of steel in molten zinc, but it has been mentioned, the steel has to fit into the bath of molten zinc. And we can coat some larger structures with this process using a technique called double dipping or progressive dipping. We put one end in the kettle and then we flip it over and put the other end in, and it gives us some leeway to do larger structures. But there is a physical limitation because the bath contains the molten zinc. Now with thermal spray zinc, it's more like spray painting with the liquid metal. We have a heat source to melt the zinc, and we use compressed air to project those drops of molten zinc onto the steel and build up the coating. So in this way, size is not an issue. We can do this process in the factory or in the field, while hot dip galvanizing is restricted to a factory application because the size is important. And here's an example of a bridge structure. I will be giving examples from North America, primarily where I'm based, and referring to North American standards. But we can see here the main structural beams of this bridge are too large to be hot dip galvanized. But all the cross bracing and support members and also the hardware, these could be hot dip galvanized. And if we thermal spray the beam and we hot dip galvanize the cross bracings, when we assemble the bridge now, the bridge components, we have zinc metal in contact with zinc metal. There's no potential for bimetallic corrosion. So both processes, hot dip galvanizing and thermal spray zinc, are very compatible. They can be used with each other without issues. Generally, hot dip galvanizing is a less expensive process than thermal spray zinc metallizing. But then again, if the size becomes an issue, thermal spray zinc metallizing is the only option to get a metallic zinc coating on the steel for the maximum corrosion protection. So corrosion protection with zinc, first of all, it's a barrier coating, just like paint. But more importantly, it provides galvanic protection. So as a barrier protection, yeah, it keeps any corrosive environments away from the steel. But more importantly, the galvanic protection, and sometimes this is accidental damage, the coating gets scratched. sometimes it's intentional. We come to an existing structure and we drill a hole because we want to bolt a sign on a bridge or something. So we can be sure that the zinc will continue to protect the steel even if there is damage to the coating. Now, we've seen the galvanic series of metals previously, again, in various forms. Anything at the top of the list will protect any metal that is below it. And so we can see I've highlighted zinc and steel there. Zinc is above steel, so it will corrode preferentially to protect the steel. We also see, you know, Simon talked about stainless steel, but another important aspect, if you have mild steel connected to stainless steel, that mild steel will corrode to protect the stainless. So be aware that there are different combinations that can produce bimetallic corrosion with one of the metal components sacrificing itself to protect the other one. But we see zinc and steel there. Magnesium and aluminum are also above steel. These three elements are commonly used as sacrificial anodes, but there is a difference. I mean, aluminum has about 1/10 of an electron volt difference from mild steel. So there's not much driving force there for galvanic protection, and it provides more barrier protection. We saw in the data that Simon showed magnesium has 1 full electron volt potential difference with steel. So there's quite a lot of driving force there. So magnesium is very reactive, very effective for galvanic protection, but it doesn't last very long. So now zinc is in the middle in that sweet spot. It has good potential for galvanic protection, but it's not so reactive that it's fully consumed. So it lasts a long time while providing galvanic protection. And we can see an example of this here. The top photo, we took some 140 centimeter long panels, and on one end, TSC, the thermal sprayed coating, for 10 centimeters, we covered with a metal, and we can see them below, some aluminum alloys, some zinc alloys, but we left 130 centimeters uncoated. And these samples were immersed in seawater, and the seawater is the electrolyte. The thermal spray coating is the anode that's protecting the exposed steel. And we can see the results there in the bottom photos. So the aluminum alloys, there's a 5% magnesium alloy. There's also a pure thermal spray aluminum. So we can see the right-hand side, the small 10 centimeters of steel that was coated, but the exposed steel is showing significant red rust here. The bottom three are zinc alloys and pure zinc that is available for thermal spraying, zinc 22% aluminum. More common is the zinc 15% aluminum. So this would be 85 zinc, 15% aluminum, and then the pure zinc. So now here we can see that small 10 centimeter of coating has fully protected 130 centimeters of exposed steel. So this is just a very graphic illustration of the galvanic corrosion potential of zinc for protecting steel. Now, if we look at the corrosion conditions in South Africa, fortunately, the South African Journal of Science published a review in 2019, and they have divided the country into various locations in order to define the corrosivity of the environment. There is a relatively long coastline, 2,800 kilometers. Generally, when we're within 150 meters of the sea, we're in an environment, an extreme corrosion environment, which is designated CX. There is an ISO designation for corrosive environments. C1 is indoors, C2 is urban, C3 is rural, C4 industrial, C5 marine, and CX extreme. So we are on any coastline generally in a very extreme corrosive environment. If we go from 150 meters to a kilometer inland, the corrosivity will depend on the surf action, the temperature, topography, wind flow, and we can see variations in corrosion rate. So one thing that was interesting here is that we have different corrosive environments along the coast of South Africa. So if we start on the east, it's a subtropical coast. Then in the south, we have what's labeled in this report as a moderate coast. And then on the west side there, the Mediterranean, and which I found interesting. But they measured the corrosion rate in all of these environments by putting mild steel panels and measuring the corrosion rate of mild steel. So on the subtropical coast in the east near Durban, they were measuring 134 microns per year. However, in Cape Town, in the Mediterranean zone, 460 microns per year, so much more corrosive. And while there is more rainfall in Durban, there's much more surf action in Cape Town. And it's this dispersion of chlorides in the air, which is more important for the corrosivity in this area compared to Durban. Also important, there's quite a lot of industrial activity near Johannesburg. So there's with atmospheric industrial pollution and heavy rainfall there, generally more than 500 millimeters per year, giving acid rain conditions. There can be appreciable corrosion rate, even though it is in an internal environment, and the zone is labeled as a moderate eastern plateau. So because of the corrosivity inland and along the coast, I think corrosion protection is important for steel structures in South Africa as everywhere. Now let's look specifically at the thermal spray zinc process. There are two technologies widely used, flame spray and arc spray, and I'll discuss those. Then we'll look at the coating structure of the thermal spray. Graham talked about surface preparation for painting. It's equally important for any coating, as you know, hot dip galvanizing and thermal spray zinc as well. How do we measure and control the quality of the applied coating, and health and safety aspects for application? So the process itself is quite simple. We have a material feedstock. We apply a heat source to melt that zinc. Then we accelerate the drop against the surface and we build up a coating. Now for zinc, we can have pure zinc. There's also a zinc 15% aluminum alloy wire. Both of these are very commonly available. There are some other chemistries, but these two are available, perform well, and most commonly used. It is a 100-year-old process. This was first demonstrated in 1912 by, I think in German, Dr. Max Schupp. So we're not talking about a new or innovative technology. This is quite well established and has a long and successful history. Now for flame spray zinc, the feed source is a wire, and this is fed into a torch, generally an oxyacetylene flame, and that melts the zinc, and then with another gas, either compressed air or nitrogen, we propel those drops onto the work surface. So the picture at the right shows the equipment required, very, very simple. On the left side, we see a little schematic of what would be happening at the torch head. So we can see the wire in the middle. We have oxygen and acetylene and a separate air source for propelling the spray of zinc. I've been advised that this schematic is incorrect. It shows a flame projecting in front of the wire when actually the flame is contained within the spray gun, so that there is no visible flame during the flame spraying of zinc. Now for arc spraying, we use two electrically conductive wires. When these touch, they create an arc, and then that melts the wires. And again, with compressed air or other gas, we can propel those liquid droplets onto the steel. So some equipment we can see on the right-hand side, a more heavy-duty installation. The wire is coming out of a barrel. In the middle, this is a more portable application. A smaller reel of the zinc wire is attached to the top of the power supply, which is very similar to a welding power supply. Now on the left-hand side, we can see another schematic. Again, here we can see the two wires, one positively charged, one negatively charged. When they meet, we strike an arc, and then we propel gas through there and build up the coating. Now, if we look at the difference between the two application types, arc spraying, and all of these graphs will be represented in a light green and a flame spraying in a dark blue. And we'll also look at the impact of the alloy, the pure zinc and the zinc 15% aluminum. If we start at the bottom left-hand side, we look at the melting rate. So we can see, independent of the alloy, arc spraying has a higher melting rate than flame spraying. First of all, we have two wires used in the process instead of one. We can get much higher heat inputs with the electric arc than with the flame. So we can melt more kilograms per hour with arc spraying than with flame spraying. Now, if we look in the center graph, the deposit efficiency, there is some particles that solidify before they impact the coating and will bounce off. So this also depends on the operator's skill, but this is less dependent on the spray technology, arc spray or flame spray, but more dependent on the alloy. And we seem to have better deposit efficiency with the zinc 15% aluminum alloy than we do with the pure zinc alloy or pure zinc metal wire. And now we finish on the right-hand side graph. Now we're looking at covering efficiency. How many meters squared per hour can we cover with a coating that's 100 microns thick? And again, because of the deposition efficiency and the spray technology, the arc spraying generally provides much faster coverage rates than the flame spraying. And so I compare this to flame spraying is like painting with a brush, and arc spraying is like painting with a roller. There are times where you actually need the detail of flame spraying as you would with a paintbrush, and other times you want to cover large surfaces and the arc spray would be more efficient. So the thermal spray coating structure, these droplets are impacting on the surface, they flatten, and they also leave irregularities on their surface, which helps anchor the next layer of drops that land on the top surface. And this is how we build up the coating. And the coating thickness is really dependent on the time of spray. So the schematic on the left here exaggerates a little bit some of the features of the coating structure. We can see there can be some unmelted particles. We can have some oxide inclusions as the zinc is atomized and projected through the air. We can have oxidation occur. We can also have voids present where the zinc particles overlap and solidify without fully filling. And then on the right-hand side, this is a cross-section through a coating, and we can see some of those features, some oxides and voids. Typical porosity or voids in a coating is less than 10%, usually about 5%. And then oxides and unmelted particles, can be another 5%. And if we do build up to a coating thickness, normally 100 microns, very similar to hot tip galvanizing, even if there is porosity or voids, they are not interconnected, and there's no through thickness porosity where any corrosive elements can get through to the base steel, even if the thermal spray coating is left on its own. Now, because we are spraying onto the steel, there is no metallurgical bond. We are talking about a mechanical bond. And this is why the surface preparation for thermal spray metallizing is very important. You have to have a very rough surface to allow that mechanical interlocking of the zinc particles with the surface on that first few layers to give us a very good bond with the steel. And it is called thermal spraying, but it is actually a cold process. There is very little temperature that is passed on to the steel, so there can be no impact on mechanical properties of the steel. There's no possibility for distortion or warping because of heat on one side of a component and not on the other. We've actually sprayed business cards when people come for visiting at a conference, for example, so that no risk of having the paper catch fire because there's very little temperature transfer during thermal spraying. So now for surface preparation, again, it's grit blasting, which is key. This is the key requirement for surface preparation. We need to have this sharp angular profile. Now, Graham had talked about the SA3, which is a white metal surface preparation. SA2.5 is a near white metal. And SP, the Society for Painting in North America, they also have a white metal or near white metal designation, 5 or 10. The same with NACE. SP and NACE have now joined to form AMP, but NACE number 1 or number 2 surface profile, this is white metal or near white metal. But the angular profile, we want to have 75 to 125 microns, anywhere from 3 to 5 mils. If there are areas that we do not want to be blasted, masking is possible and common. We can put tapes or rubber mats on an area of the steel structure that we're blasting so that the surface is not roughened. But generally, anywhere we are going to coat with thermal spray zinc, we want to have this sharp angular profile and a clean surface. So conditions for blasting, just like paint, we have humidity and dew point considerations, a little bit more forgiving than for paint. We can have humidity up to 85%, surface dew point greater than 3 degrees Celsius. Graham had mentioned dusting and also chlorides. You know, we want to clean that surface after blasting so that we have no chlorides or dust present before we encapsulate them in the zinc. Although again, the zinc will be more forgiving than a paint. So ideal abrasives are high quality garnets, and these can be mixed in a 30, 60, 80 mesh blend. Again, large softer abrasions produce a bumpy surface more than a sharp and angular surface. It may be clean, but it will not have the angular surface profile, which is important. And in the shop, where abrasives can be recycled, we have seen successful use of steel grit, although usually we prefer garnet. Now, after we blasted the surface and we want to ensure the quality of that surface before we apply the zinc, we do some non-destructive testing. This is generally a tape test. We try to apply the thermal spray within 4 hours of blasting, but if we are in a controlled environment, this window can be extended many hours or days. Mostly this is in a shop environment, although there has been very good field containment where we are able to extend the time from blasting to spraying for whatever reason. But for surface profile measurement, there is an ASTM tape test D4417. This is a standard test method for field measurement of surface profile on blast clean steel, very specific to the application. We put a tape on the surface, we burnish it so that it takes on the profile, and then we can measure the profile on the tape. Now we're ready to thermal spray. Again, we have very similar atmospheric conditions, humidity up to 85%, a surface dew point. Now, Graham had also mentioned duplex coating. So if we are just spraying zinc on the steel and we'll leave it, we want at least 200 microns of metal sprayed on the surface. But if we are going to seal that and paint it to make a duplex coating, we generally will put 100 microns of zinc, and then we will cover that with a paint top coat. With thermal spraying, each pass of the gun generally provides 100 microns of thickness in any case. So with just one pass, we can be ready for painting or sealing. And there is no curing time with thermal spray zinc. It is ready to be painted immediately after application. But if we want to only use the thermal spray zinc for corrosion protection, we should have a slightly thicker coating or twice the coating. So that will mean reapplying another layer of zinc. Now we can use thinner zinc with the painting because now the paint adds barrier protection onto that zinc, and the zinc will remain untouched as long as the paint is available. Along with testing the surface roughness, we also want to measure the coating adhesion after the zinc has been applied. Another ASTM test, D4541, standard pull-off test. So now with pure zinc coatings, we generally achieve higher than 3.5 megapascals, and the zinc 15% aluminum has slightly higher. We achieve better than 5 megapascals of pull-off strength. Again, these are significantly higher than most paint bond strengths. There is a standard bend test for measuring ductility of materials, but there is no accepted test for metallic coatings. So there is a generally accepted practice to spray onto a steel coupon and do a 180 bend test around a ½ mandrel. We can see some cracking here. Cracking is acceptable. It is flaking that registers as a failure in the bend test. So we've talked about a duplex coating, putting a paint top coat on top of thermal spray zinc. The sealant really fills the porosity at the surface so that, and also is sometimes called the tie coat because it aids for the paint adherence, although the rough surface of the thermal spray zinc is an excellent anchor for any paint coating. So again, this will extend the life of the thermal spray zinc coating by adding another barrier coating. So the paint will protect the zinc, but now the zinc will also protect the paint if there is, again, a scratch or a hole through a duplex coating. We saw an example where if we have paint on steel and we scratch through, the iron will begin to rust. And iron corrosion products can take up 7 times the volume of the iron. So this puts enormous pressure on the paint film. So at those edges, it can't withstand that pressure. It starts to peel up, and we get a phenomena called underfilm creep corrosion. Now, if we have the paint on zinc and we scratch through, even if we scratch through to the base steel, the zinc will protect the steel from corrosion, so we don't get these high volume iron corrosion products. We will start to get the zinc corrosion products, but as shown, these will tend to build up in the crevice. So we don't get the pressure on the paint film. So the paint stays intact right up to the scratch or hole. And so in this way, while the paint gives extra barrier protection, the zinc also protects the paint. So we get a much improved longevity of the combined coating. Now, when we do make a duplex coating, the coating thickness measurement now becomes very important. Most magnetic gauges will measure the total thickness of the coating. So that is the thermal spray zinc and the paint layer. So it's important to measure the thickness of the zinc as it's applied to make sure that it meets the specification, generally 100 microns. And then afterwards, when the paint is applied, measure the total coating thickness, subtract the thickness of the zinc, and then we make sure that the paint coating thickness also meets specification. And we are finding one of the common errors is the paint is applied too thin. So using an electric gauge, they measure a coating thickness. It's the zinc and the paint combined, but the paint contractor may only think that he's reading the full thickness of the paint. So it's important to know the thickness of both coatings. And some thickness gauges now can differentiate between the metallic zinc and the paint on one reading. Some defects for thermal spraying: thin coatings apply the zinc and the paint to the specified thickness. I talked about incomplete melting of zinc. This is called zinc spitting. You have to adjust the wire feed rate to match the heat input to ensure complete melting. Generally, this is a very gross defect. It's quite obvious. We will have lumps of zinc sitting proud of the thermal spray zinc coating. The remedy is very simple. We just sand the coating. It removes those lumps of zinc. There's no need to recoat, or they can be left there the surface quality is not an issue. If this is the interior beam on the bottom of a bridge, you just have more zinc available to help with corrosion protection. But if it's an exposed beam and we want to have a smooth surface, we can just sand those defects and they will disappear. And then poor adhesion. Again, the surface preparation is quite important. We must have a sharp angular profile. We must spray at the proper distance to ensure that we have good adhesion to the steel. Now, all of these topics that I've talked about, surface preparation, etc., are well documented in this standard. This is a joint standard from NACE, the American Welding Society, and SSPC. It is NACE standard number 12. It is American Welding Society standard C2.23, and it is the SSPC standard CS23. So this is for the application of thermal spray coatings of aluminum, zinc, and their alloys, and composites for the corrosion protection of steel. So this covers all aspects of the process: the coating application, surface preparation, repairing, measuring, adhesion testing, and then painting and top coating. There are other standards as well to make sure that the operator is qualified. Another American Welding Society standard, C2.6, Guide for Thermal Spray Operator Qualification, and an ISO standard, approval testing of thermal spraying. Here, a number of sample coupons are sprayed, the roughnesses of the surface is measured, the thickness of the coating is measured, and then you can have an examination and be approved as a qualified thermal sprayer. Especially for arc spraying, there are some health and safety requirements. It is treated as a welding process, so there is some dust that is developed. So we need a full respirator helmet with positive pressure inside that keeps any dust from entering the helmet. And the fresh air supply is recommended. I say necessary. Do not use any industrial compressors or air supply. This should be fresh air. There is UV radiation produced by the arc, so we need eye protection and then body protection as well. We can have a sunburn from using arc spray, so protective glasses, clothing, gloves, sunscreen. And there can be some noise produced as well from the compressed air, so ear protection, whether that's earmuffs or earplugs. So a photo showing some factory application. Here we have two operators, one on top, one underneath, manipulating the thermal spray guns to coat this steel beam. This is a field application. This is a very old bridge. We can see some of the riveted connections. So we can do field repair. This paint has been blasted and removed, and now the thermal spray zinc is being applied. We can see some of the containment here to make sure any of the dust from blasting the paint, because now those paint residues can be a hazardous waste and they can be collected. And importantly for the zinc, if there is any zinc overspray, this can be recycled. This is a valuable zinc metal product, and there is a market for the recycling of zinc. So we want to contain that and collect it and keep that metal value. My first case study here is the Memorial Bridge. This is in New Hampshire. This crosses an ocean passageway. This bridge had several innovations. As a truss structure, they removed the gusset plate where the beams join, and they made one single integral part of steel to better handle the stress at this location. And they moved the bolted connections away from this area. This also helps with corrosion protection. You know, one part of corrosion protection is design. We don't want to have water pooling at the lowest area of the connection where generally a gusset plate will be and all the connectors are there. So not only do you have the stress of the bridge structure, you can have pooling water. The structure on the left-hand side of this photo, this is a lift bridge. It's actually in the middle of the bridge, but remainder of the bridge is shielded there, but this portion lifts up and down to allow ocean-going vessels to pass into this channel. And this bridge was completely thermal sprayed, and there was no sealer applied. This was just massive zinc applied to the steel. So every day they did quality testing. So we've talked about both of these tests. We can see the bend test. This is a thin steel coupon that will be sprayed every day by the operator. So this is a way to ensure the qualification or quality of the operator, and then also the quality of the work. This will go through the bend, and again, cracking is acceptable, but flaking is not acceptable. On the right-hand side, we see the adhesion test. And actually, we're doing the adhesion test, but we've also done a surface preparation test on these panels. So we can see it's a much thicker, large, square panel of steel. This was abrasive blasted, and then they did a tape test, and we can see the two tapes that have been applied to this panel. That front end of the panel is masked, and then we spray the zinc onto the surface. Now we will do the pull-off test on the zinc. So these tests are conducted daily. We can see there's a pile of samples in the right-hand side in the background there. So they're doing replicate tests in order to ensure the quality of the operator and the quality of the coating. So the steel was sprayed in a factory, then it was delivered to the site for installation. And we can see here one of the beams that was delivered. This was all assembled with hot dip galvanized bolts. And so again, we have zinc on zinc. We have no issues for bimetallic corrosion. We can see the overlap of these connections here. We will have zinc in that gap. And again, this is very important. It will eliminate or greatly reduce any potential for crevice corrosion, which can usually start in these locations. Now, an overview of the bridge again. The specification called for a thicker coating at the bottom of the bridge, which is closer to the salt water, and a thinner coating above the bridge deck, which would be in a less corrosive environment. So I've added the orange line, the orange dash line to this image here. So we can see below the specification was for 14 mils or 350 microns of zinc, and 15.8 or almost 400 microns of zinc on average was applied to this section of the bridge. And then above the bridge deck, specification was 10 mils or 250 microns, and in actual fact, 12.7 or 318 microns on average was applied to the top surface of this bridge. This bridge was installed in 2013. It does have a 120-year design life. We're coming up to a 10-year anniversary. There's no rust or staining at all evident on the bridge as of yet, and it is expected to meet its design life with no maintenance. Norway, I talked about how Norway is using duplex coatings since 1965. So we have very good data from Norway about the performance of duplex zinc coatings. And I'll do a comparison here between a bridge that was built in 1962 and it was only painted, and another bridge that was built some years later, but with a duplex thermal spray zinc and paint coating. So this bridge in Brevik, in Norway, it's 750 meters long. It's a cable suspension bridge. It has a steel truss structure underneath the bridge deck. It has a 40-meter clearance over the water. So that classifies it. Again, we had test coupons on the bridge. It is a C3 corrosion environment. The bridge was built in 1962 and painted with the traditional paint system, which at the time was an alkyd paint. Through the decades, it had several paint maintenance schedules. In 1992, 30 years after initial construction, it was completely renovated. They changed the paint system to a more robust, a zinc rich primer, an epoxy barrier coat, a polyurethane top coat. Although still, we can see after 9 years, we had some corrosion evident. And then in 2013, after 21 years, the bridge was fully repainted again. And if we look at these photos at the bottom right-hand side, we can see some of the original rivets, but we can also see that new steel has been bolted in place. So this bridge has needed paint maintenance, but it's also needed structural maintenance because of corrosion. Now we compare this with the Rombach Bridge. It's the exact same design and size. It's 750 meters long. It's a cable suspension bridge. It has the steel truss structure underneath and also about a 40-meter clearance over the water, the same C3 corrosive environment. This bridge was built in 1964 and it was actually left uncoated for 6 years. So then we did a field application of the thermal spray zinc and paint. This was a pure zinc coating, 100 micron thick with a sealer. Graham had talked about not applying alkyd paints to zinc, but almost all the bridges in Norway from 1965 through to 2008, I think, when they changed their, were alkyd paints. There was an intermediate coat and then a top coat. The inset photo at the bottom was taken in 2010. This is 40 years after the initial construction. Again, these overlapping riveted joints are prime locations for crevice corrosion, and there's no rusting, there's no staining at all. The performance has been exceptional. Now, we can look at the maintenance cost for these two bridges to get an idea about life cycle costs. So the Brevik Bridge is in orange and the Rombach Bridge is in blue. So if we look at time zero, we can see for the Brevik Bridge, it was 30% less to paint that bridge compared to a duplex coating. Although we had the first paint maintenance of that alkyd paint after 13 years. So after 13 years, the duplex coating became cost effective. Then we had more paint maintenance until 30 years after. Now here, the paint system was changed to the zinc rich paint, epoxy and polyurethane. And then we went 21 years. So we can see the improvement in the different paint systems, the alkyd paint. If we look at also paint durability databases, the alkyd paints have an average life of 12 years in a C3 environment. So we went 13 years, very close to the paint durability index. The more modern zinc rich primer, epoxy and polyurethane paint, they have a expected life of 18 years in most paint durability indexes. Here we went 21 years. We're in the ballpark, but on the good side. But now if we look at the Rombach Bridge, so here we can see it was more expensive to apply. We're applying a zinc coating as well as the paint coating. So there is extra cost there, but we were maintenance free for 42 years. And if we look at the total life cycle cost now, after 50 years, because we've eliminated paint maintenance, we have half the life cycle cost with a duplex coating compared to a paint-only coating. Something else to consider when we do paint maintenance, generally the steel has started to rust. Anywhere from 5 to 10% of red rusting is a trigger point to initiate paint maintenance on a steel structure. Now the duplex coated bridge, we initiate paint maintenance when the paint starts to fail. So not when the steel exhibits rusting. So we saw some photos of the Rombach Bridge. I'm going to bring that back here. So this was at 40 years. The steel is in excellent condition, but we painted it after 42 years. So did the coating catastrophically fail over those last 2 years? Well, it did not. But if we look at some horizontal members near the bridge deck, some debris from the roadway has abraded the paint top coat. And so we can see the mid coat coming through. So then it was repainted. So this is also a maintenance philosophy by the Norwegian Public Road Administration. They use very highly contrasting colors between the top coat and the mid coat. So it's very evident. when the paint needs maintenance. And so they will be very proactive and they will maintain the paint. The zinc is never consumed and the steel never starts to corrode. If we use the same criteria of 5 to 10% of red rust evident on the structure, this could probably be left for 100 years before we even start to see red rust, because after 42 years, we have some damage to the top coat, but the mid coat is still in play. The zinc would have to be exposed and consumed before we start to see red rusting. So significantly longer life with the duplex coating. I think if this maintenance philosophy was transferred also to paint-only structures, use highly contrasting colors between a mid coat and a top coat, take action when the top coat needs attention, not when the steel starts to corrode. And again, you could reduce maintenance significantly and extend the life of structures by being a bit more proactive. I think also the graph shows the difference. You know, we have paint, which is like pie. We can have cherry pies and apple pies and banana cream pies. There's a smorgasbord of chemistry for paint. Then we can put zinc into those chemistries. Zinc rich paints outperform normal paint. Then I think we get to metallic zinc coatings, again, more complex to apply, but much longer corrosion protection. And then finally, the duplex coating, putting the two together, the zinc adds an extra layer of barrier protection to protect the zinc, and then the zinc protects the paint from underfilm corrosion. We can get extremely long life from these coatings. A final point I wanted to mention, Graham had talked about paint outperforming zinc in neutral salt spray testing, and this is true. We saw the development of the coating on zinc. When it's exposed to air, we get oxides, hydroxides, and carbonates forms. It's a very complex surface chemistry on the zinc, but that gives it the corrosion protection. But when we put it immediately in a 100% humid salt spray test, those protective layers never get a chance to form. And so if you are just comparing salt spray test of paint and zinc, the paint will appear to be performing better than the metallic zinc coating. But all the evidence we have from real life examples, zinc metallic coatings by far outperform paint only coatings. So just a warning to be aware that not all laboratory tests can be extrapolated into real world performance. So with that, I will finish. So I hope I've shown that the metallic zinc and zinc thermal spray coatings in particular provide excellent corrosion protection. The zinc is a barrier protection, but it also adds sacrificial corrosion protection. That galvanic action is quite powerful in protecting steel from corrosion. And then zinc thermal spray coatings are portable. They can be applied in the factory or in the field. And we saw this with the Rombach bridge. So size is not an issue if there are limitations on your steel structure to use hot dip galvanizing. So thank you very much for your attention. And I'll now be happy to take any questions.
Thanks very much, Martin, for bringing us up to speed on how to use zinc thermal spray as an anti-corrosion protection for steel on bridges, structures, and ships. Before we continue, I would just like to share with you an informative video on the power of zinc thermal spray for corrosion protection. This video shows wind turbines that will be exposed to severe atmospheric conditions and are designed to last 25 years.
Yeah, I had some wind tower examples I could have shown, but it has become the default coating for offshore wind towers. The first offshore wind towers off the coast of Denmark were thermal sprayed and painted, a duplex coating. They had a design life of 25 years, and they were 25 years at sea with no corrosion, no staining, and that has become the default for offshore wind.
Thanks very much for that comment, Martin. I think, Simon, I'm not sure if you'll agree with me. We've gone slightly, well, quite a bit over time. So I was wondering if maybe, since there are no Q&A questions in the actual question and answer section, if maybe I can just hand over to you for some closing remarks. And then if anybody has any questions, they can email us. And then we can answer you via email. You can send perhaps an email to zinc@iafrica.com, and then we can connect with people after the webinar. What do you think, Simon?
Shannon, can you just show us what the results of your survey were?
Certainly. Let me share that with you. Right, can you see them?
Yes.
Okay, so as you can see here, for the question, do you recommend zinc-rich paints for projects? 100% say yes. Good news. Why do you specify zinc-rich paints? 13% say because it's easy, 56% because it works, and 31% because the steel is in situ. Do you use inorganic zinc-rich paint or organic zinc-rich paints? And 56% of people who answered say inorganic, with the other 44% saying organic. And have you ever specified zinc thermal spray for steel on projects? 50% yes, 50% no. Are you considering zinc thermal spray for a marine application? 31% of answers say yes, with 69% no. And then just some information on those who would like the IZA or specialized coatings to contact them. We will send you those details afterwards.
Shannon, thank you very much. I think we've really gone over the time here, and there have been a few comments, but no, I can't see any direct questions. If there is anybody now, then they must speak now or forever hold their peace. But if
well,
not,
I did see two questions in the comments, and one was about repair of hot dip galvanized steel. And I think zinc-rich paint can be used for that. Thermal spray zinc can also be used. And there's a third product, a zinc solder, that is available. So there are options for repairing damaged hot dip galvanized steel. And another one about can the voids of thermal spray zinc be removed by wire brushing? And I would say no, this is not possible. I think wire brushing might break some of the protruding zinc and push it into a void. But through the thickness of the coating, there will always be some voids there. They are not detrimental to the corrosion protection, but the wire brushing will not eliminate them. It might mask the problem by, as I say, covering them on the top surface.
There is one comment somebody mentioned on surface preparation. No mention has been made on removal of chlorides, sulfates, and nitrates, or holding the blast. This is a critical step missed. Martin, can you comment on that?
Yeah, I think I did mention removal of chlorides, maybe not specifically sulfates and nitrates, but that is in the American Welding Society standard. There is a measure for dust cleanliness and chloride level. So whoever made the comment is correct. This is an important step.
All right, thank you very much then. And then I think, Shannon, we've just about wound it up. Martin, thank you very much for coming out, being with us from all the way in Canada, and your superb presentation. Then to Graham Stead from Expectancy. Graham, thank you very much for presenting on zinc-rich paints and your products that you've formulated for repairing galvanizing. And I'm sure many of the listeners and those attending will want to contact him. And then to Shannon and the team at Creamer, thank you for putting this all together, getting it all electronically set up. And then to all of those who attended, all those 34 guys and still ladies are still here, and the others who were on, we had 70 odd, we had 80 registrations. Please apply for your CPD points and fill out the form. We also have a publication called a rapid guide to galvanizing and essentials of galvanizing. And we have 6, we're busy with 6 emailers on all aspects of zinc and coatings. So please ask us if you'd like them. Thank you very much, everybody. And we look forward to seeing you again. We intend to have probably another webinar later this year. Cheerio and goodbye.
And on that note, I'd also just like to say thank you very much to our panelists, as well as to Simena for arranging the CPD points. As Simon mentioned, you can send us your registration number if you haven't already done so. Thank you very much to everyone for attending. If we didn't get a chance to answer your questions, send us an email, zinc@iafrica.com, or you can send it directly to me, shannon@creamermedia.co.za. And don't forget to get your electronic or hard copy of the Essentials of Galvanizing and Rapid Guide to Galvanizing. You can send me an email and we can send you those. They are an invaluable source for engineers. The recording of today's webinar will be sent to you in due course. And if you have any additional questions or need any help with corrosion and zinc, please get in touch with Simon Norton at zinc@iafrica.com. And as Simon mentioned, look out for the next webinar in 2022. More information will be available on the Engineering News website. And don't forget to specify zinc by galvanizing your steel using zinc rich paint or by using zinc thermal spray. We look forward to hearing from you soon. Keep well and goodbye.